The basic principle here is electrons are confined. They are stuck inside the oxygen molecule in the room, bouncing off the walls. The electrons are stuck around the nucleus by the electric force because they're attracted to the nucleus. So electrons are confined. Wavelengths, they have a wave nature, and the wavelength must fit. I know that it doesn't always seem obvious by the wavelength must fit. I mean, if I start talking about an oxygen molecule bouncing off the walls, I'm kind of using my screen here. I hope the edges of my screen count as the edges of yours as well, bouncing backwards. I think fitting is fine there. The idea that we're going to have half waves, that's 2 half waves that I've just drawn, or 3 half waves, that sort of thing. They fit in, that's fine. The idea that it's in a circle and it's got to fit, admittedly, that feels a little bit weird. What do we mean by fit then? One way of imagining this, suppose that's the orbital around the nucleus. Imagine that you cut it out on a piece of paper, so you've got like a little ring here, and then you snip the ring and open it out to be like a string. It's got to fit on the string. That way of imagining the process of having it fit. So the wavelengths must fit, and only wavelengths fit. Therefore, because wavelength links to energy, only certain energies are allowed. That's why we have orbitals. And that's why we don't have orbitals anywhere and everywhere. We only have orbitals in certain positions because we only have orbitals in certain positions. The energy that they have in that position gives them a wavelength that fits. If I drew a nucleus there, and I drew one orbital there and another orbital, then what that means is if an electron is at that distance away, then basically if you look at this system here, I've got a proton or a collection of protons and a negative electron. So I've got one charged object and another charged object. Now I think some of you have done this and some of you haven't done this. The A-level students have not done yet electric fields. I think all that's done in the second year. But the IB, I think Christine, I have a vague memory that Christine indicated that you've done the electric field. If I take a positive charge and a positive charge, there'll be a force of repulsion. A negative, force of repulsion. Positive and negative, or the other way around, force of attraction. That's what we've got going on here. We've got a force of attraction. If I take a positive charge and a negative charge a certain distance apart, there will be a force between them, and the force is given by F is K Q1 Q2 over R squared. Now for a certain distance there is also a potential energy. It's just like if you had a mass a certain distance from the Earth, you could say, or the surface of the Earth, or wherever you want your zero to be, you could say it's got gravitational potential energy. Well, a positive charge, the nucleus, and a negative charge, the electron, they're a certain distance apart, and that will mean a certain electrical potential energy. And the energy is linked to the wavelength. So what you could do if you wanted to try and work out where do I think the orbitals will be, what you could do is use these ideas and say, let me just move forward to a page that's got nothing on it. You could say, right, okay, there is my positive nucleus. I'm going to zoom in on it. Don't want to do that. Let's suppose that an electron could be there. would mean a certain distance apart. That distance there, if the electron is going to go around like that. So what you can do is use the distance. So look at the distance and work out what's the energy, the electrical potential energy. Equation, if you want to know it, is electrical potential energy is K Q1 Q2 over R, or in this case D. That's the equation. We do it in the 7th form with A level, and again, it's kind of up to Mrs. Edwards. I'm not quite sure. Have you met that one yet, Christine, or not?
Yeah, we've done these equations.
Okay, there's 4 equations. They all look really similar to each other.
Yeah, we've looked.
Do you not remember 4? Yeah, it's this. It's F is K Q1 Q2 over R squared. E is F over Q, which is K Q over R squared. V is K Q over R, and EPE is K Q1 Q2 over R. They all look really similar, which is why they're guaranteed to cause mistakes in an exam. And if you start with the wrong equation, there's no error carried forward. You lose all the marks. So it's really important that what I just did there, you all need to, not now because you haven't done it, unless you have, but you definitely need to practice it. So Paul, I will be hassling our group if we have the same group to memorize those. Not that I'm teaching this. Okay, so anyway, let's get back to this. So the nucleus and an electron, and we've pretended that the electron is okay there. We just pick a value for D. Okay, work out the energy. From the energy, so by knowing D, we can work out the energy, and that allows us wavelength, because the energy and the wavelength are linked. It's not quite as obvious as we've had before, but we have seen, when we did all the de Broglie stuff, we have seen that wavelength and energy are linked. For those of you who need a reminder of that, we had Ke is P squared over 2m, and P is H over lambda, so that's 2m lambda squared. So there is a link between energy and wavelength. Well, this is not quite the same equation, but it's the same principle. There is a link between energy and wavelength. We don't need to worry about what that link is. I'll talk about that in just a moment. Okay, so you work out a distance, you pick a distance, and you say, right, what's the energy? Okay, so distance gives us energy. Then what you do is you say, okay, if that energy, what's the wavelength? So now I have the wavelength. And then I say, does it fit? In other words, if that circle there, if that circle, it kind of fits perfectly on it. Correct. If it does, if it fits, orbital. If it doesn't fit, it's not an orbital. Now let's suppose it doesn't fit, because it probably won't. Then what we do is we say, okay, let's get rid of that. Let's get rid of all that lot. Let's pick a new distance. We'll go for a slightly bigger distance. We'll do exactly the same thing. We through that, and do we get that or do we get that? Doesn't fit. Okay, let's try a bigger distance and a bigger distance. And you imagine that basically we can draw a line like an x-axis or an r-axis. Basically, everywhere along there, we are constantly saying to ourselves, what's the energy? Therefore, what's the wavelength? Does it fit? And there will be certain points where it fits, where the energy is a certain value that gives us a wavelength that then fits. And those are the positions of the orbital. So the reason that an electron cannot be in any of the other positions around the nucleus is simply, and it is, I guess, the idea is wacky, but the process is very simple. It's the idea that it has to have energy that gives it a wavelength that fits. And that's what these are. These are the energies that allow it to have a wavelength that fits. And all these other positions, they can't be in. So when we zoom in here, this electron here, it could not jump up to there because it has a wavelength that does not fit, and that's not allowed. So in order to agree with wave-particle duality, it forces us into a position where we only have certain orbitals. And we normally represent that with what we call an energy level diagram, which is that. Okay. And one of the things that we said was, when you move from an individual atom to an individual solid, we raise the what happens to the energy levels, and the answer is they become energy bands, because as you add more and more atoms to the system, each atom brings an orbital to the hybridized orbital, but they have to have slightly different energies so that they are different, because you can only get a maximum of 2 electrons in an orbital. It just doesn't make sense if they don't have different energies. So, because if they had an identical energy, it'd be the same then. There's got to be something that's different about them, different states. So, and that led us to the idea that in a solid, the hybridized orbitals create bands. And then the final part of this sort of puzzle of how does this link to metals was, all you are interested in is what the situation is at the top of the energy level structure. Well, the energy levels become bands, so I should say the energy band structure. And there's only really 2 options. You are either in a situation where it's this, where you have a completely filled band and then a gap before the next unfilled band. Now let's just not lose sight of what we're saying here. In the individual atom, this situation would be an orbital that's full. It's got 2 electrons. Don't forget, they only have 1, 2. Empty, half filled, fully filled. So in the individual atom, this would be an orbital that's got 2 electrons in it, and the next orbital up, which is effectively a representation for that, has no electrons. That's the one situation. The other situation is where there's 1 electron in the outer orbital, which when it becomes a band, hybridized orbitals, it looks like that. It's still hold. And the next one up, again, is empty. Now we are only interested in the very top of the energy spectrum. And so it is worth just, I think we said this last week, but again, I'm desperate for you to try and get a good understanding of this. It is worth just reiterating why it's important to realize that we are only talking about the top of the band. And the answer to that question is very simple. The energy that an electron can gain as a result of you applying a voltage and making a current flow in a circuit, the energy that you can gain is only about that amount. That little dot, I've made it too big now, is about the energy that can be gained by an electron from an electric field. Now, if you look at that, that gives us a problem, because this band is filled with electrons. And if I just move that to the side, if that, I've made it a bit too big, but it doesn't, it's because of my pen. If that's the amount of energy, if that's the height, remember what happens when an electron is accelerated by a voltage. Voltage is applied, that produces an electric field. The electric field produces a force on a charged object, and the force makes the electrons accelerate. So their energy rises. In other words, they move upwards in this structure. They go to higher energies when they get accelerated. Then they hit an atom, they lose some of their energy and they drop back down again. So in this picture, what is happening when electrons take part in current flow is they're rising and then falling and then rising and falling, and it's of electrons that rise as they accelerate, then they hit an atom, lose some energy and fall. But the problem is, all that up. The problem is that if this is the amount of energy that can be gained from an electric field, a tiny amount by comparison, then these electrons here at the top, these electrons can't do anything because that them, let me make my pen a bit smaller. An electron here, it would place him maybe there, but he can't be there because that's like trying to be in an orbital where you have an energy that doesn't give you a wavelength that fits. Electrons can't be in this region. There are no orbitals that give them wavelengths that fit in that. It's like the gap between the orbitals. In order for the electron to make use of the electrical energy, it's got to be next to empty levels, and it isn't. It's got to make a big leap like that, and an electric field will not do that. That's why this situation, what we say is that the phrase that is used sometimes, really, the phrase that is used sometimes, sorry about that, the phrase that is used sometimes is that filled bands cannot carry a current, or filled bands cannot take part in conduction. So half-filled bands are different. If you look at half-filled bands, they're fine because I've got an electron sitting there and it's got lots and lots of empty orbitals next to it. Lots and lots of empty options in the band next to it. So it can accelerate and then get knocked down and accelerate and get knocked down. So an half-filled band can take part in the conduction process. So there's no conduction here, and there is conduction here. But you also need to remember that even here, even in this situation, the only electrons that can conduct are the ones at the top of the energy spectrum. Like that electron there cannot conduction because it would require it to jump up to maybe there. And it can't do that because it's filled, because those states are filled. So it's only a relatively small number of electrons that actually take part, which is why we end up in this situation where the lie that we gave you in the past, the lie that we gave you is that insulators, we normally talk at GCSE of metals or conductors and insulators. That's it. We now know that actually there's a third type in the middle. There's conductors, there's semiconductors, and there's insulators. Now, semiconductors and insulators are basically the same. They are situation here on the left. In a semiconductor and an insulator, your energy structure is that your top situation, your top band with electrons in it, is completely filled, and there is a gap called the energy gap. It's not really a difficult idea, that one. It's a gap in energy, an energy gap. If the energy gap is not too big, so 1, 2, 2.5 electron volts, something like that, then what it means, and the importance of this, it means that although the electrons can't take part in conduction if you apply a voltage, thermal energy, energy associated with the vibration of the molecules in the substance, is enough. If the temperature is high enough, it's enough to provide enough energy for electrons to leap across the gap. And then, of course, they can take part, because they are next to unfilled, take part in conduction. So if the gap is small enough that thermal energy, the term is promote, can promote electrons across the gap, we call that a semiconductor. But if the gap is too big, so that the kind of temperature that you would need would basically destroy it, like you'd need like 10,000 degrees. Well, no solid is going to be solid at 10,000 degrees. There isn't anything that is holding itself together 10,000 degrees. We call that an insulator. It's the difference between a semiconductor and an insulator is all about the size of the band gap. It's not a cutoff. It's like below this, it's an insulator. Sorry, above this, it's an insulator. Below this, it's a semiconductor. It's not that straightforward. It's a bit vague. And it's all about generally whether thermal energy can promote the electrons or not. Now, we're here. This is fine because this is just electrons here. And this band here is completely irrelevant at the top. Completely irrelevant because this is where the action is. But again, it's a very small number. So when we said insulators basically don't have free electrons, conductors do. That's the difference. I can remember standing in the lesson saying that to Sid. Metals and other conductors have free electrons. They're good at conducting. Insulators don't. Well, this was a lie. They all have free electrons. Free electrons are electrons that are in hybridized levels, which on this system means a band. Okay. Now we distinguish between free electrons, which have got nothing to do with whether something's a conductor or not, and conduction electrons. Conduction electrons, which at GCSE you would say are the same thing as the free electrons. Now we know the difference. Conduction electrons are electrons that can take part in the conduction process, and that is a tiny, tiny number of electrons by comparison with the number of free electrons that are in the material. Right. So what do we move on to? This we've already mentioned this. We've already talked about the fact that the energy is very small. And conclusion, filled bands cannot conduct electricity, half-filled bands conduct electricity, the size of the gap, blah, 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 blah. All right, okay. So let's put some numbers in. Let's put some numbers. Oh, I don't know, 260. Let's do some calculations. A couple of very simple calculations. Okay. Temperature. What is average kinetic energy of electrons? How do I work that out?
Isn't it 3/2 kT?
3/2 kT. That's 3/2 times by 1.38 times 10 to the minus 23. If you can try and remember some, it's quite useful. It looks good. So if you can remember speed of light, that's good. 3 times 10 to the 8. If you can remember big G, the universal gravitational constant, 6.67 times 10 to the minus 11, that's pretty good. The other two, there's 4 constants worth trying to remember because they come up quite a lot. Planck's constant, 6.63 times 10 to the minus 34. And Boltzmann's constant, 1.38 times 10 to the minus 23. Right, okay, multiplied by the temperature needs to be in Kelvin, and let's say it's 20 degrees. So that's 293. Okay, so if I do that, and if you've got a calc, it might be worth you doing it as well, just so that we can confirm we got the same answers. Oh, sorry, Paul, how's your hand?
I'm getting it off the cast tomorrow.
Oh, it's tomorrow. Sorry. Hey, do you know what day it is on Wednesday?
No.
I can't hear anything there. That's really sad.
No, I didn't hear what you said. Did you ask me what's on Wednesday?
What? Yes, special day. Wednesday is a special day.
I don't know what's happening on Wednesday.
It's my birthday.
I did not know that.
Well, you do now. Right. Okay. So what? 6 point. Okay, that sounds like I'm like asking you to send me a present. I'm not. Okay. 6.07 times 10 to the minus 21 of a joule. How do I get that in electron volts? How do I turn that into electron volts?
You times by 1.6 times 10 to the minus 19, is it?
Okay. Let's suppose just for a second that the answer was actually 1.6 times 10 to the minus 19, not 6.07 times 10 to the 21. How many electron volts is that?
1.
Yeah, that's 1 electron volt. If it was 3.2 times 10 to the minus 19, how many electron volts?
3.2. No, 2.
Sorry, Christine? Yeah, 2 electron volts. Get 2. So that's the energy. How do I turn that into 2?
Divide by 1.6 times 10 to the
Right.
minus 19.
Yeah, not multiply by, divide by. So when I do 1.6 e to the 19, I get 0.038 electron volts. Yeah, which is about a 26th of an electron volt. Okay, so that's quite small, but and probably average kinetic energy. Probably I'm going to be using the energy in joules in a moment. We'll see why that's important in a moment. Right. Okay. Now I know. Let me just remind myself what we said. Yeah. Okay. Pen would be good. We know that the kinetic energy of a free electron. What do we mean by a free electron? No, in a solid. Explain that to me. That term, free electron. What does that mean?
It's in a hybridized orbital.
Excellent. It's in a hybridized orbital. Yeah. We know that the kinetic energy of a free electron is given by Ke is h squared over 8 ml squared into nx squared plus ny squared plus nz squared. Now, what I'd like to do is I'd like to basically say, let's suppose we're looking at an average electron. In other words, let's suppose that we can use that energy for the energy here so that we can work out the quantum numbers. So what are the quantum numbers? If you remember, when we at quantum numbers, we said the lowest one was 111, and then it was 121, 211, 112, and that was 3. That was 4. That was 6. The next one was 9. That's 1. Is it? No, that's 11. The next one was sorry, it is 9, and it's 2, 2, 1, 2, 1, 2, 1, 2, 2, etc., etc. Well, let's work out what the quantum numbers are here. How high has the average electron gone in the energy level structure? So we know that the kinetic energy of a free electron is given by this. Okay. 4 electron. And by an average electron, I basically mean, i.e., its Ke is the average Ke. just to get me a rough feeling, for an average electron, what are the values for the quantum numbers nx, y, nx, ny, and xn? And what I'll do is assume that nx equals ny equals nz. Just because if I excuse me, if I don't do that, I'm going to end up working out a value for nx squared plus ny squared plus nz squared, and then I'm going to have to try and work out, you know, what integer values are going to combine to make that work. If I just assume, as a rough feel, if I just assume they're the same, it allows me to work out a value. So, which is an album, of course, by Peter Gabriel. We've got 6.07 times 10 to the minus 21 is equal to h squared over 8 ml squared into 3 n squared. Just nx squared plus ny squared plus nz squared. If nx and ny and nz are the same, that's 3. Okay, well, we need a couple of other numbers here. So anybody know what the mass of an electron is?
9.8 times 10 to the minus 31.
Ooh, you're so close. I can taste it. 9.8, did you say?
Is it 9.81?
You drop, that's, yeah, it dropped into G.
Yeah.
0.11 times 10 to minus 31, but it was so close. Well done. 9.11 times 10 to minus 31 of a kilogram. So I got now I need an L, and this is slightly tricky. We need a physical size for a piece of metal. So yeah, I mean, I want it to be sensible. Like, I don't know, a bit of wire, 10 centimeters, something like that. A metal rod. Let's just assume it's 10 centimeters, which is 0.1 of a meter. Okay, and what I want to do is I want to work out n. So we've got that n equals flipping heck. So this is 6.07 10 to the minus 21 times 8. Oh gosh, I haven't written this small enough. Hang on. Blimey. So got n equals, I'm going to put a square root around it in a minute. I'm just working it out for n squared. 6.07 times 10 to the minus 1 times by 8 times by 9.11 times 10 to the minus 31 times by 0.1 squared, divided by, okay, 6.63 times 10 to the minus 34 squared. That's a killer. Times by 3. I don't think the 3 is going to make a big difference. I think that's it, isn't it? 8 ml squared. Yeah, I think that's it. Square rooted. So let's have a look. That's Pinnock. Okay, I'm going to do square root of that lot, and it's 6.07 e to the minus 21 times by 8 times by, that's plus 8 times by 9.11 e to the minus 31 times by 0.1 x squared divided by 3 times by 6.63 e to the minus 34 squared. Woo! Anybody got a number?
.72 times 10 to the minus 10.
No. 10 to the minus 10? That's less than 1. That can't be right.
Oh, I got that.
You can't have a small number. You can't have a number less than 1. The smallest number is 1. The number, if I look at it, it looks like 6 is about 10 times 10 to the minus 21. About 10. 9.11 is about 10 times 10 to the minus 31. And that's 10th squared, so that's 100. 10 to the 2 on the bottom. 6.63 squared, that's 36. That's 10 to the minus 34 is 10 to the minus 68. Times 3. Oh, hang on a minute. Because 6.6 squared is like 30 something. 6 is a 36. 7 is a 49. But it's times by. There's about a 10 there. So,
So
okay, so that cancels with that.
I got a 1.8 times 10 to the 6. 1.8 times 10 to the 6.
Okay, now I've got something very similar to that. Let me just check my numbers. 10 to minus 31.1 squared, 6.63, 10 to minus 34. I've got something really similar. Christine, what about you?
I haven't got a calculator on me, I'm afraid.
Okay, well, if I do,
Yes,
how can you not have a calculator?
So I saw what I did. I forgot to square Planck's constant at the bottom. I've got something similar.
Always the killer.
Yeah.
What you got?
1.8 times 10 to the
8.
6. Yeah, similar to Paul, I think.
Yeah, I get 1.8 times 10 to the 7. So, and I can't see. Have you got an? Is it a graphical calculator? So can you see your calculation?
No, mine's just a normal scientific one.
Yeah, let me.
I've got minus 31 there and minus 21 there. That's minus 52 on top. And then take
You
on
know,
the
it's
bottom
to
and take it up to the
the. I
top.
got it to the 7th.
So that's 16. So that's isn't that going to be?
No, I
Isn't
got
that
it to
going to
the
be
7th.
10 to the 16? Square rooted is like 10 to the 8. Okay, so and I've got 1.8 times 10 to the 7. So sorry, Paul, what was you saying?
Yeah, I just did it again. I don't know why I didn't change it. I must have missed. I got to the 7 as well, but I don't know why. Even though the
I get 1.8 times 10 to the 7, which is 18 million. Okay, thing to note is this is a big number, and we're talking 1, 2, 3, 3, 3, 3, 3, 1, 3. When we did the the business about degenerate against energy, and it's kind of like to the half, and I went up to 40, maximum number 40. Well, this is big time bigger than that. I mean, this is not 40. This is like 18 million. Okay, so what's the significance? This is huge, and therefore the degeneracy is also expected to be very large. Because remember, degeneracy is proportional to E rooted. The number of states, should not produce. I don't know why I'm sorry. The number of states should not produce significant problems for the electrons at the top of the energy spectrum. Now, what do we mean by that? That means that when you've got those electrons at the top, it means that if one of them jumps up into a level, I don't mean across a band, across the gap, there's more than enough. The degeneracy is more than large enough that another one can go into the same level. Just because there's so many that's remember what degeneracy is. It's the number of states. A state is an orbital, effectively, with the same energy level. So the degeneracy is so big at this value that it's quite easy for electrons to be excited into the energy levels, and they're not going to get in each other's way. Then it's not going to be a situation where one electron has gone up and another electron would like to go up, but it can't because it's kind of filled. You know, if there's already one in there and another one goes in, it's full. Another one can't jump up. So it means that at the top of the energy spectrum, the electrons can be excited. Okay. If we took the metal to Kelvin, if we took the metal to 0 Kelvin, we have, and this is the way that we would G, and this is number of electrons at different energies. Now I'm going to copy this and put it over here. Right, because I'm going to use it in a minute. Basically what we have is this. And what I've drawn here is these are the electrons. Now what I've drawn in that diagram is this is the number of electrons, different energies. And although it looks like it's going to 0, don't forget it can't go to 0. These are for the free electrons. So this is for free electrons. This is not the core orbitals with the core electrons. This is free electrons. In as Sid said, in the hybridized orbitals. When you look at the number of electrons that have different energies, it must follow the shape of the degeneracy, because basically the electrons, once they're in an orbital, once 2 of them are in an orbital, that's it, it's filled. So you can almost imagine that the energy level structure is created when you make the solid, and then you pour your electrons in, and they will start from the lowest energy, and that means as close as they can get to the nucleus, and they will just fill up. And because they're not allowed to occupy the same state, in other words, you can only get 2 electrons in an orbit, is worth 2 states. What happens is it fills up, and then it's just like almost like a glass of water. You end up with a highest possible energy. We have a name for that. That energy. Oh, I want it to be red. that energy is called the Fermi energy, named after Enrico Fermi. So what is the Fermi energy? The Fermi energy is the largest energy a free electron can have at T equals 0. Now, what happens if we raise the temperature? If the is increased, then what happens is we give the electrons energy. The electrons gain energy. And what happens is this goes like this. It goes up. Okay, I might have a problem here because my dog is about to attack me. Imagine that that's the Fermi energy. What happens is this. And the point is, a relatively small number of electrons at the top of the energy spectrum are excited. So it's the same, it's a slightly different way. In this bit here that we were talking about, where only a small number of electrons actually take part. Can we measure this? Oh, I'm not going to write any more about that. Can we measure it? No. Sorry, I'm lying. Yes, we can. If you theoretically would try to work out the specific heat capacity of a metal, you assuming the free electrons can take the energy, then what you end up with is a theoretical specific heat capacity that's very large because there's huge numbers of electrons. Because atoms are so small, so if you have a lump of material, you've got a large number of atoms, which means you've got a ridiculously large number of electrons, and they can all take the energy. Which means the idea is they can all just like go up in energy levels. The trouble is they can't do that because the electrons here cannot get excited because those states are already filled. It's because of this business of, you know, only certain number of electrons. You only excite at the edge. So actually, if you work out the specific heat capacity of a metal, it's nowhere near as big as you would theoretically predict if all of the free electrons were taking part in absorbing energy and moving faster because of the thermal energy they gained. It's a tiny, tiny number. Okay, so I think I'm stop our discussion of metals there, because I think we've got a lot of information there that's way beyond A level, and I think what you need to be aware of, and I think this is going to work better for Sid, if I'm honest, because he's doing advanced chemistry. Already met the concept of like 1s and 2s and 2p and 3s, 3p, 3d, etc., etc. I think the most important thing to get from this is that quantum mechanics has led us to that materials have a wave nature, matter has a wave nature. And when we investigate that in detail, it turns out that for any confined particle, it has to be, if it's going to be confined, it has to be that its wavelength has to fit. That requires only certain wavelengths to be allowed, so only certain energies are allowed. When we look at what energies are available, it turns out that for a free particle within the confining space, so obviously it's not free when it hits the wall, but for a free particle, there is a kinetic energy equation which is not that difficult to generate. H squared over 8ml squared into nx squared plus ny squared plus nz. Obviously, if I was in correct. If I was in 2 dimensions, I'd lose one of the quantum numbers. If it was 1-dimensional, I'd lose the other one. That's where we started, 1-dimensional oxygen molecule. We just ended up with an N. So this is true. This equation is valid for free electrons in hybridized orbitals in a metal or in an instance, in any solid. Okay, so how does degeneracy feed into this? Well, when you start putting the electrons into the orbitals in the band, the states is probably the nicest way of saying it. Remember, a state can take 2 electrons. The problem that you have is that the degeneracy down here is not so high. There aren't so many states available. So once they're filled up, when you have that bottom state, which is like 1, 1, 1, once you've got 2 electrons in there, it's filled. The next one up had 3. That will take 6 as a maximum. Once they're in there, that's it. That's it. There's no more possible, which means these electrons, if you can only give them that amount of energy, they cannot be excited. The next one was another 6. The next one was a 1, I think. Was it 12, I think? Oh no, there's an 11, which is 3, 1, 1. That's another 3. If these are filled in a real material, because I mean, what's this? This is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. There's only 22 electrons there. That could be 22 atoms with 1 atom in the outer hybridized. Lithium, that's like 22 lithium atoms. That's nothing. I know if the amount of energy that I can give to the material from, let's say, an electric field is only that amount, that height, there's nothing I can do with any of these electrons. They cannot be excited, because if they were given this amount of energy, it does not take them to empty states. The next ones are up here. Only these can be excited. I've drawn 3 there, it should be 2. So the issue of degeneracy becomes important because it limits how many electrons can actually be excited when you're trying to give them some energy. And when the degeneracy is low, like it is here, that's a massive. If the degeneracy was high, let's suppose it isn't. Let's just suppose that the degeneracy of this second was like 1 million. Okay, well that means I've got loads and loads of states, or stretching all the way over here, loads and loads and loads. These electrons can then be excited, not a problem. Some of these electrons drop down. If I cooled it down so all these electrons start dropping down into those, because there's 1 million, makes no difference. These electrons can still be excited. If your degeneracy is enormous, opportunities to excite your electrons without problem. The problem is degeneracy is not huge, except when you get to very high energies. So all of the electrons over here have to be excited. They would love to take part in the conduction process, because there's a voltage which creates an electric field that creates a force. There is a force acting on them, but they cannot make use of the energy because the degeneracy isn't large enough to allow them to have empty states next to them that they can be excited into. So degeneracy, if you like, a limiting effect that restricts what the electrons can do. And the ideal situation would be that actually the degeneracy is like ginormous, but it isn't. So this is why it's only at the top. The problem of degeneracy creates a problem where only the electrons at the top of the energy spectrum can actually be excited, and that's like a major issue. And what we'll do, what I do every now and then, is come back to this idea and just make sure that you've kind of got it sorted in your head. So please, if I ask questions like Sid did earlier, and what do I mean by a free electron? If you're not sure, just go for it. Don't ever feel that you can't try and have a go at answering the question. If you get it wrong, that's what, I'm not going to have a go at you. You know that. We need to get used to using these words so that we can try and be in a better situation to be able to describe them. Okay, and what I'd like to do now is just, I am going to stop now because I realise that, you know, because of the revision course I'm running this week, it's kind of messed up our timings for 1 week only. What I'd like to do is just give the title, which is The Death of a Star. And that's going to be the next thing we do. And what I'd like to do now is how the concept of degeneracy is used to explain how stars die. Yeah. Well, this is also a reason, by the way, why metals are hard. One of the reasons why metals are hard is because if you take a metal and you try to squeeze it, you're doing work on the metal. You're putting energy into it. You're using your chemical potential energy and you're putting it into the metal. And what will tend to happen then is the electrons and the atom will all get excited, will rise to higher energy, because it's the reason why if you compress a gas, the gas gets hot. Because you've done work on the gas. Well, same thing for a metal. If you grab a metal and you try to compress it, you're trying to put energy into the electrons and the atoms in the metal. The problem is you can't do it because you don't have enough energy to be able to do it because of the issue of degeneracy. Degeneracy limits how much energy can be taken in. Limits how many electrons can make use of your energy. So when you squeeze and you try to make the electrons rise to higher energy levels, they can't do it. It's a quantum mechanical effect. They'd like to, they can't. You can only excite a tiny number, which means the metal will not take on a greater energy because it's not capable, because basically almost all of your electrons are effectively frozen in the energy states that they're in. And that makes it hard. You squeeze it and it won't take the energy that you're trying to give it. And we're going to find out that when a star dies, the core that is left behind is also called hard. So we don't have to know huge amounts about astrophysics, but we do have to know a little bit. So I think the next 2 sessions will be the death of a star.
That's all, folks.